Hi everybody, it's time for video 4 in lecture module 5 where we will start our exploration of the planet Mercury. Let's go ahead and dive right in and take a look at what the planet looks like. So here we are looking at the planet Mercury. This image is taken by the NASA Messenger spacecraft, which is a recent mission that went and explored the planet Mercury, giving us some of the best views that we've ever had of the planet and doing all sorts of fundamental science, which 100% revolutionized our understanding of Mercury. Mercury went from a interesting but not super interesting world to perhaps one of the most fascinating planets in our solar system, with lots of mysteries contained within it. And a lot of those mysteries have fundamental parts that play out in our story of how our solar system formed, the specifics of it. So if you were just to look at the planet Mercury, I could probably tell you that this is the far side of the moon, and you'd be like, all right, Dr. Lindsay, I guess so. I mean, it looks like it. The moon and Mercury both being airless bodies, they have just been sitting around having their surfaces exposed to outer space for about 4 billion years, just accruing impact craters. So they are airless worlds that are dominated by impact craters, which makes them look remarkably the same. A feature that you can help me pick out this is Mercury is this right here, what's called the Caloris Basin, a very large impact basin on Mercury. What does Mercury look like compared to the Earth? And a side by side, so this is 38% the radius of the Earth. Earth is much, much bigger than Mercury. Mercury is the smallest of our terrestrial planets. And to really go ahead and put it into perspective, there is our moon for a scaled comparison. Mercury is not that much larger than our moon. It is larger, but not by a whole lot. Let's talk about some of the basic data. I do expect you to generally be able to recognize, if I give you the AU distance away from the sun, you should be able to know what planet I'm talking about. However, I don't expect you to memorize all of these numbers. So how far away is the first planet from the sun? So Mercury's orbital distance is semi-major axis. How far away it is from the sun on average is 0.39 astronomical units, or 0.39 AU. How big is the planet? It is 2,440 kilometers in radius. That makes it 38% the size of the Earth, or 0.38 Earth radii in size. Makes it 1.4 times larger than the moon. As I was saying, it is a small planet, and it's really not that much bigger than the moon. It is the smallest planet in the solar system. It wasn't always the smallest planet in the solar system. We had to get rid of Pluto first, but it is the smallest planet in the solar system. It's also the lowest mass planet in the solar system. If you actually want to know the number, it's 3.3 times 10 to the 23rd kilograms. That doesn't make a lot of sense to me. It's easier for me to think about things in terms of mass of the Earth. And that comes out to be about 0.055 or 5.5% the mass of the Earth. So it is a really, really, really small baked potato. We would have expected that, being such a small baked potato, that this planet would have cooled down significantly, would have lost any liquid metallic core, and therefore not have a magnetic field. But it does have a magnetic field, so we are surprised that it does have a magnetic field. It's a very weak one, about 1% the strength of Earth's, but it is there. It does have a planetary dynamo that generates a global magnetic field. Is the planet differentiated? Well, let's play the game that we have been playing, and let's look at the average density and compare it to the density of the surface rocks. So the average density is 5,400 kilograms per cubic meter. We do not have samples of Mercury's surface. I'm not even sure if we have any meteorites from Mercury. I doubt it. That'd be really, really hard to get them from Mercury to Earth. But we do know the composition of the surface, so we do know what kind of rocks are there, and we know the densities of those rocks. They come in as just sort of your normal average rock, about a density of 2,500 to about 3,000 kilograms per cubic meter. Significantly lower than 5,400 kilograms per cubic meter, which instantly tells me that in the interior, towards Mercury's core, there must be some very dense material to bring its average all the way up to 5,400 kilograms per cubic meter. In other words, Mercury is differentiated. Let's look at its orbital period. You could go ahead and use Kepler's third law. You could plug in this number, p squared equals a cubed, and then convert the answer you get in years to days, and you would find out that it has an orbital period very close to exactly 88 days. A little bit less, but 88 days is close enough for here. How long does it take for Mercury to rotate around exactly one time? Its rotational period, its sidereal day, is about 58.6 days long. A very, very slow rotator and a very small baked potato. So yes, we are very surprised about that global magnetic field. Does Mercury have an atmosphere? No, it doesn't, meaning that the only erosion it has is the generation of regolith, which means that its surface is going to be dominated by impact craters, which means that we can trace out the history of Mercury by doing crater counting. We can actually date the surfaces very easily using crater counting. Does Mercury have any moons, natural satellites? No, no moons of Mercury. Let's start by taking a look at Mercury's orbit. Again, its semi-major axis, its average distance away from the sun is 0.39 AU, 39% of the distance between the Earth and the sun. However, Mercury has a noticeably eccentric orbit. It's pretty easy to see that this blue orbit that I've drawn over here is not a perfect circle. It is a squash circle. In fact, Mercury has the highest eccentricity of any of the planets. It comes in at a value of 0.2056, about 0.21, which means that it has a significant difference between its perihelion and its aphelion. At perihelion, Mercury is only about 0.31 astronomical units away from the sun, while at aphelion, it is about 0.47 astronomical units away from the sun. So a huge difference in how close it gets to the sun. And this is going to have some interesting effects on Mercury. One, at perihelion, being that much closer, is going to have about 2 times the amount of energy from the sun falling on it. So if we're talking about that energy in, we have the solar constant for Earth. We're talking about the solar constant for Mercury. At perihelion, it's going to be twice that as it is at aphelion, which gives Mercury a different kind of seasons, but without an atmosphere, you don't really notice the seasons really on Mercury. Another interesting effect is, let's go back, we talked about the tides on the Earth and the tides, or the tidal bulge of the moon and the tidal locking process that made so the moon always points the same face at us. What about the tidal effect of the sun acting on Mercury? And here we see something interesting. When Mercury is here at perihelion, the tides drawn from the sun, so the tidal force, is about 3.5 times stronger than it is here at aphelion. So the tidal forces acting on Mercury from the sun are very large here, 3.5 times larger at perihelion than at aphelion. This is going to be an important part of the story, so go ahead and catalog that information. We will be revisiting it shortly. But we're still taking a look at the orbit. And one of the things I introduced in the previous video is the concept of greatest elongation. So just a quick review. So elongation, if you draw a line from the Earth to the sun, and then you draw what we call a line of sight from the Earth, where draw the line so where you'd see the planet. That angle between the sun and the planet is what we call elongation. So greatest elongation is where that angle was the largest, and it's where this line would fall tangent to this curve, which is a little bit closer to the Earth than this midpoint right here. And since Mercury has a noticeable eccentricity, the greatest elongation angle for eastern elongation, Earth would be rotating around like so, so east is this way. So the greatest eastern elongation is only about 18 degrees, while the greatest western elongation can be up to about 28 degrees. So with Mercury, we have to talk about the maximum greatest elongation, and that ends up being 28 degrees. So why is this important? What does this mean for Mercury in the sky? If you're trying to go outside and look at Mercury, it's always going to be close to the sun. In fact, the angle between the sun and Mercury at maximum can be 28 degrees. So Mercury is always located within 28 degrees from the sun. Now let's just do a little bit to try to figure out when we could actually observe Mercury, because very, very few people have knowingly ever observed Mercury. Estimated about 0.01% of the population of Earth have ever knowingly looked out, seen a point in the sky and go, oh, that is Mercury. So maybe you want to join and increase that percentage and join a very rare and exclusive group and observe Mercury. So let's consider it at greatest western elongation when it's 28 degrees away from the sun. Well, you can do a quick calculation and realize that the Earth rotates about 15 degrees per hour. So in 28 degrees, that gives you about 2 hours where Mercury will be above the horizon, where the sun is setting or has set or is rising or has risen, where it's actually getting dark enough so you can see Mercury. You get at best a 2-hour window, making it one of the most difficult planets to observe with the naked eye, of course. If you can't see a planet with the naked eye, it's very difficult to observe with the naked eye. And I want to go ahead and show you, just so you know what things like this would look like in the sky. So I brought up stellarium, and I went to one of the points of greatest western elongation of Mercury. This happens to be on the 11th of April in 2019. I turned off the atmosphere, so it looks like it's nighttime. And that's just so we could see everything very easily. So here is the sun, and a full 27.7 degrees away, we have Mercury, meaning that right here, Venus probably has an elongation of about 28 or 29 degrees in this image, but we can see Mercury at greatest western elongation. It is the angular distance between the sun and Mercury. Okay, now we have to get into some pretty nuanced things. So bear with me for a second, and I want to talk about Mercury's orbit and its rotation. Let's go ahead and run through a little bit of logic. Mercury's been sitting there for about 4.5 billion years, and it's very, very close to the sun, which has an enormous mass. We know that the sun draws tides on the Earth, and Mercury is a lot closer to the sun, and the force of gravity it falls off, or the tidal force falls off with distance cubed. So the tidal force of the sun acting on Mercury is going to be enormously larger than the tidal force of the sun acting on Earth, which means that the tidal force acting on Mercury is so large and Mercury is so small that over 4.5 billion years, Mercury should be tidally locked to the sun. Remember, with the moon, that means that the moon always points the same face towards the Earth. The moon has a synchronous orbit. It rotates exactly once for one orbital period. This is what we called a synchronous orbit, and it was the effect of the moon being tidally locked to the Earth. So we should expect Mercury to be tidally locked to the sun. So we should expect its rotation period to equal its orbital period. Mercury's orbital period, and I've put the precise number here because I'm going to use it here in a minute, is 87.9691 days. And this was the assumed rotation period until we developed techniques of using radar to measure the rotation of Mercury. This is using the Doppler effect. You shoot a beam of radio waves, all of the same wavelength at Mercury, which will be rotating around and around and around. The radio waves will bounce off. The part that's rotating towards will be blue shifted, away, red shifted. So you get a spread of wavelengths, and that spread gives you the rotation rate. We found, to our surprise, that Mercury had a rotation rate of 58.646 days. Now, that is a surprise because it's not a synchronous orbit. And I want to go ahead and show you something right here, because remember that whenever there's some external force acting, something like a tidal locking, then we expect things to end up in nice integer ratios. So let's go ahead and play around with these numbers. Me being a math geek, I like to play with numbers. So I am going to share a different screen really quickly. And I'm going to bring up a calculator. All right. So what I'm going to do is I'm just going to compare the orbital period of Mercury, 87.9691 days, and I'm going to divide it by its rotational period, 58.646 days. Almost exactly 1.5, a 3-to-2 ratio. Huh. Interesting. Very, very interesting. So Mercury does not have a synchronous orbit, but it does have a nice ratio between its orbital period and its rotational period. The tidal locking process, the physics says that it should have happened. So yes, Mercury is tidally locked to the sun, but not in a synchronous orbit. How is this actually working? What is creating this to happen? So here's what I just put in the calculator. The orbital period divided by the rotational period is almost a near exact 3-to-2 ratio. So Mercury has what we call a 3-to-2 spin-orbit resonance. What a mouthful, right? 3-to-2 spin-orbit resonance. Here's this new term, spin-orbit resonance. Oh God, I have to memorize all this for quizzes and exams. Oh, what a weird term. Wait, okay. The term itself is telling me the answer. Mercury has a 3-to-2 spin-orbit resonance. So that means it spins 3 times for every 2 orbit. Okay, I can handle that. So a 3-to-2 spin-orbit resonance means that Mercury will rotate 3 times for every 2 orbits around the sun. A 3-to-2 spin-orbit resonance, 3 spins per 2 orbits. The answer's in the name. So hopefully that helps you understand this sort of gobbledygook word right there. And as I was just saying, anytime that we see this nice ratio, a 3-to-2 ratio between things like orbital periods and rotational periods, this does not happen by chance. Something needs to be forcing it. And whenever you have these nice ratios we call them resonances. Kind of like playing a chord in music, where you have resonances that are going on. In this case, we're talking about a resonance between the orbital period and the rotational period. So we can use this terminology and say that the moon's synchronous orbit has a 1-to-1 spin-orbit resonance. Okay, so now we have all the parts of spin-orbit resonance defined. So why does Mercury have a 3-to-2 spin-orbit resonance? And the result, why this is, comes down to the fact that Mercury has a high eccentricity, which means that if you remember Kepler's second law, it travels at different speeds as it goes around the sun. And since whenever it's at perihelion, it'll be traveling the fastest, it's also the closest, and that's where the tidal forces are the strongest. At aphelion, it'll be moving the slowest, and the tidal forces are the lowest, the weakest. So if I had to make a choice, where am I going to tidally lock to? Am I going to tidally lock to how fast I'm orbiting around the sun at perihelion, or how fast I'm orbiting around the sun at aphelion? Nature is going to choose where the tidal force is the strongest, at perihelion. So Mercury is going to get tidally locked to perihelion. So to go through some of this, I've tried to put together a little demonstration here. We'll let this be Mercury. I've put a plus on one side, a minus on the other side, and I want to play around with this 3-to-2 spin orbit resonance. One, it just makes Mercury have a weird day. So the plus will be perihelion, and this will be the tidal bulge, the blue part here. So it would be trying to stretch out the planet towards the screen and towards me. So as Mercury goes around the sun with a 3-to-2 spin orbit resonance, and one orbit around the sun, it would spin around 1.5 times. So by the time it reached its next perihelion, we'd be looking at the opposite side. And then after one more orbit around the sun, it would spin 1.5 more times. So whenever it comes back around, we would be looking at this side again. Well, instantly, this already tells me something rather strange. One solar day from noon to noon on Mercury is 2 Mercury years. Weird. Mercury has some weird things going on with it, and that's a weird day. But now, let's think about what's going on and how this nice 3-to-2 spin orbit resonance, where after one time around, we see this side. After a second time around, we see this side. In both cases, the tidal bulge is in the direction of the screen and towards me. It's pointed towards the sun. That is where we want it to be at perihelion. So by locking itself into 3-to-2 spin orbit resonance, by pointing the tidal bulge towards the sun where the tidal force is the strongest at perihelion, it makes it so that every time it passes perihelion, the tidal bulge is in the direction of the sun. That is how Mercury is tidally locked. So at every perihelion passage, the tidal bulge is stretched in the direction pointing it directly towards the sun. Did it have to be a 3-2 spin orbit resonance? No, it could have been a 5-2 or something like that. It could have been some other number. The why is exactly a 3-2 spin orbit resonance is one of the things that we don't fully understand about our solar system. But out of all of the models that have been run, it is the one that happens most frequently, and it is a natural way to end the tidal locking game. So there we have it. And then finally, I want to give you a little bit about global views on Mercury. And you know what? That was a pretty long video with a lot of information. Why don't we go ahead and save global views for a bonus video number 5? So I'm going to go ahead and stop this video right here, and I will see you for a short video where I'm going to try to highlight and show you a lot of beautiful pictures of the surface of Mercury.